You look at the equations, the moment some people see equations they get worried. Here there is nothing to worry about these equations, because you are now experts in understanding what we are talking about. C centered lattice gave you H plus K odd absent. So suppose now you simultaneously, you see you cannot have a center and a B center and leave it at that, because by symmetry C center will automatically get centering also done, therefore it becomes a face centered lattice. So either you have a C, A or B centered lattice which is representing the monoclinic and the orthorhombic systems, or you will have a face centered lattice which can come in, of course monoclinic special case F can be coming in, but we can convert it, which will be probably indicated in some TA class. Then we have the F center coming in orthorhombic, F center will come in cubic as well. So depending upon the other symmetry elements we can decide what crystal system it has to go into, and apart from the fact that we have ABC alpha beta gamma, which is also indicators of what crystal system a given crystal goes into, given system goes into. So these are the 4 equivalent points in case of F centered lattice. We have xn, yn, zn. This will be equivalent of to xn half plus yn half plus zn. This represents the A centered lattice. Half plus xn half plus zn yn, this represents the B centered lattice. Half plus xn half plus yn zn represents the C centered lattice. So when all these faces are centered we have a face centered lattice. So we again do the calculation. So what we do is again now we divide this into the 4 equivalent points, the number of atoms in the unit cell. So m now becomes n by 4. So the summation now is over 1/4 of the total number of atoms in the unit cell. So the effort becomes lesser when we have a F centered lattice. So the f of HKL is now sum over 1 to m. We have the general expression f of n exponential 2 pi I hxn kyn lzn, and then to this we have to add the centering of each one of them. This represents the A centered part, this represents the B centered part, and this represents the C centered part. So A face is centered, B face is centered, C face is centered, and therefore the expression now becomes sum over 1 to m of xyz associated with xyz, that is taken as a common factor from all these 4, just as we did in the case of the C centered. We have more expressions here, and therefore that becomes 1 plus exponential k plus l h plus l h plus k. So this expression comes up, and this expression now can be substituted with minus 1 to the power of k plus l as we calculated in the previous case. Exponential with these 2 integers can be easily evaluated mathematically, and the mathematical solution tells us that this can be 1 minus 1 minus 1 minus 1, and therefore we get this expression for f of HKL. So what do you think will happen when we have face centered lattices? Face centered lattices, as we see, there are 4 equivalent points which develop because of the face centering. So that means where the set of atoms we are considering now is reduced to 1/4. So this 1/4 atom now will repeat based on the nature of the centering. So what will happen to this expression? What would be the actual f of HKL? F of HKL, if HKL are all even or all odd, then k plus l, h plus k and h plus k will all be even, right. So for example, if you take the value of HKL to be, let us take an example. Let us take this example of reflection 1 1 1. Okay, so this tells you h is 1, k is 1, l is 1. So I take this reflection 1 1 1. And now this reflection 1 1 1 has to be fitting into this equation, and how it fits into this equation we will see in a minute. We will go to the next slide and come back again. This slide tells me that if F, H, K, L are all even or all odd, so our 1 1 1 is all odd, okay. Then if you add H plus K, it is 2. So K plus L will become 2, H plus L is also 2, H plus K is also 2. So they will be all even. So if it is even, let us say if it is 2 2 2, then also these quantities will be even. So reflections like 1 1 1, 2 2 2 will, if HKL are all even or all odd, this value will all be even, and then the calculation will be 4 times this quantity. So the structure factor will have a value whenever this possibility occurs, and for all other things it becomes 0. For all other HKL values it becomes 0. So the HKL values like 1 1 1, 2 2 2, 3 3 3 or combinations of other kinds of odd values, that is like 3 1 4 cannot be there, 3 1 3 yes, 2 2 6 yes, 2 2 1 no. So such absences therefore will develop, and so this is the statement: if H, K, L are all even or all odd, then the value of H plus K, K plus L and H plus K will all be even. Then you get this systematic absence. So this is correct. This is the way you have to look at it. So if HKL are all odd or all even, the summation of each one of the two components will become even, and therefore this exists, this expression exists. That means the systematic absences now will be enormous, and many of them will be absent in this F-centered lattice. In fact, this is something which is given later to you in powder diffraction as a what should we call a thumb rule. The thumb rule is that if you have a crystal system which is a simple primitive lattice, or if you have a system which is centered, maybe face centered, the other one is body centered. Suppose there are 3 polymorphs. This is with respect to the pharma people as well as materials people. If it is 3 different polymorphs, one crystallizing in a primitive cell, another crystallizing in a face centered cell, the third crystallizing in a body centered, it is quite possible. If such a thing happens, then if you take a powder diffractogram of this material, you have the same material, okay. If you take the powder diffractogram of the same material, you will see more reflections from the primitive and less reflections for the body center, and further less reflections for the face center. So that is how, if you record the pattern of sodium chloride, you will get only 5 peaks in the powder diffraction pattern. So the more simplified the powder diffraction pattern is, it represents the symmetry that can be associated with the centering of the lattice. Centering of the lattice is the one which will now reduce the number of possible reflections, and therefore the number of possible observations you can have. So more the symmetric the space group is, the less is the number of observations you will have. And this is an issue which we may have to tackle when we are dealing with diffraction, both in single crystal as well as in powder. And we will discuss that when we actually do the experimental analysis of these, particularly in powder diffraction. This will be very crucial. Right. So now we will take a realistic example. So you can also say the English language is rather difficult. That is why there is always a problem in getting this statement correctly. So if HKL are neither all even nor all odd, so we can use that phrase as well. So what happens if HKL are neither all even nor all odd, then it will be the systematic absence. So the systematic absences therefore will now, if you add neither or nor here instead of all or, then you get to the definition of the systematic absence. So what you should remember here is that in a face centered lattice, you add the 2 indices, add H and K, add K and L, and also add H and L. When you do that, they should be always even. Whatever be the value of H, K and L individual values, when you add 2 values, it should always be even, and when those values are even, you will get a reflection, you will get the measurement of F of HKL. So that means you will get an intensity I of HKL. All other intensities are 0. So, by just looking at the diffraction pattern now and looking at after indexing, you just easily, it is so easy now to find out the centering of the lattice. We will take an example to illustrate this systematic absences by taking the structure of zinc sulfide. In fact, it is the mineral zinc blend. Zinc sulfide exists in various forms. So, we will take the zinc blend. The mineral zinc blend, it has been found by crystallography that there are 4 zinc sulfide units in the unit cell. So, the compound ZnS occurs 4 times inside the unit cell, and that is the information we have from determining the density of the crystal. Then we determine the volume of the unit cell by determining ABC alpha beta gamma. So, we do the powder diffraction experiment or single crystal experiment, look at the x axis of the powder diffraction and find out the 2 theta values, and from 2 theta values you calculate the d values, and from there calculate ABC. So, the value of ABC will tell us now that this zinc sulfide system is going into the crystal system where there are 4 molecules in the unit cell. So, that means 4 zincs and 4 sulfur. So, when one solves this structure, we will take the solved structure so that we can illustrate the occurrence of the systematic absences very clearly. So, when we solve the structure and we show the projection of the zinc blend. So, zinc is at 0 0 0, sulfur is located at 1/4 1/4 1/4. So, zinc is at this position. So, this zinc appears at the end of the A axis as well as end of B axis, and then it also appears at the half the distances along the axis, and then the sulfur because we are already checking out that zinc sulfide is phase centered. Okay. Now, let us see what happens to the systematic absences. So, what happens to the reflections which come from zinc sulfide? Zinc sulfide is zinc blend is a phase centered cubic lattice. Okay. So, we have zinc at 0 0 0, sulfur at 1/4 1/4 1/4. So, if we look at this is the projection diagram down 0 0 1. So, this is very clear now, this distribution of atoms. So, we will see what happens to the structure factors, or in fact the intensities, and therefore the structure factors. See, what is very important now is that we are directly getting the expression for the structure factor, which now can be undergoing a Fourier transform to give the electron density. What we are not worried about at this moment still, which we should worry about, is how to determine the phase. We have the value of Fn, we have the value of H, K and L. We do not have Xn, Yn, Zn. In this example we are taking, we have Xn, Yn, Zn. So, we can get the expression for f of HKL, because we can get the expression for I of HKL, and from that we can get the expression for f of HKL. So, remember that part, because what we are now trying to discuss is, given the structure of zinc sulfide, which zinc is sitting at 0 0 0, sulfur is at 1/4 1/4 1/4, how do we get the systematic absences satisfying the F centered lattice? That is all we are now examining, and that we can see from this set of equations. You see, f of HKL is equal to 4 times Fn exponential Hxn plus Kyn plus Lzn. That we know now, because from the previous slides here f of HKL is that expression. So, we take this expression and we have written it down here. Now, how many atoms are there in the unit cell? That is the summation 1 to n. Total number of atoms is 1 to n. Now, the number of atoms here are only 2. There are 2 atoms we associated with the structure. Mark my words, the unit cell has Z equals 4. So, there are 4 zinc atoms and 4 sulfur atoms associated with the unit cell, but with the structure there is 1 zinc and 1 sulfur. So, the summation has to be done over 2 of them, 1 for zinc and 1 for sulfur. Okay. So, here m is 2, therefore, f of HKL is 4 times f of Zn. Zn is at 0 0 0. So, just like our cesium chloride example, the phase associated with it is 0. Now, Fs is sitting at the position 1/4 1/4 1/4, and you know how to do this calculation now. It will come at H plus K plus L by 4. So, this is now the expression for zinc sulfide the structure factor expression for zinc sulfide. So, there are 4 such zinc sulfide units. So, it is 4 times FZN and so on. So, there is a little error in the textbook here. We have taken it from the textbook. M is actually 4. Once we write 4 here, it is okay. Then M is equal to 2 is correct. There is not an error. M is equal to 2, Zn and F of S is the scattering factor associated with sulfur. So, there are 2 atoms with zinc sulfide, zinc and sulfur, and the summation is done over those 2 atoms. But 4 times, because we have now are going to distribute this into 4 equal parts, one coming from XYZ, another coming from the half plus X half plus Y, another one coming from half plus Y half plus Z, and the last one coming from half plus X half plus Z. So, therefore, we get into 4 such values, and then we calculate the intensity. See, eventually what we see in the diffraction pattern is the intensity, or for that matter the powder pattern will give us the intensity I versus 2 theta. So, we have to calculate the intensity. So, when we calculate the intensity, it is F of HKL square. So, 4 becomes 16 now, square of that. F of Zn cosine 0 plus F of S cosine H plus K plus L by 4 to square. So, this now adds up in case of each one of these. So, F of whole square plus F of Zn sine 0, Fs sine 2 pi H plus K plus L 4. So, what we have done here is to express it as a cosine plus sine function. Remember, we are looking at the intensity. So, there is no imaginary component that gets associated with it. So, this gives us the solution to the problem. We get the intensity value as 16, F of Zn plus F of Fs cosine 2 pi H plus K plus L by 4 whole square plus this. So, this quantity therefore is something which we will have to now see what are the possible reflections that come. Now, why I am showing this? I am showing this because zinc and sulfur, even though they are F centered lattice all right, because of the fact that there are only 4 units of zinc and 4 units of sulfur, they are sitting in special positions. Because they sit in special positions, effectively you will say more systematic absences. The major systematic absences are coming from the F centered lattice, but the fact that zinc and sulfur are sitting in special positions, they will also add to the possibility of systematic absences. So, remember, we have been discussing systematic absences in terms of lattice centering so far. We will also discuss the systematic absences which will come because of translations associated with the 2 unscrew axes or any screw axis and glide planes. This is with respect to the symmetry elements. But once we have these symmetry elements identified in the space group, we already know that there are some what we call as special positions. So, these special positions therefore will have additional systematic absences. So, if atoms have to be confined to special positions, then the structure will show over and above the systematic absence required for the symmetry. It will also show systematic absences because the atoms are sitting in special positions. This is something we will write down now as the value. So, it is either 16 F Zn Fs squared whenever H plus K plus L is 4n, and if H plus K plus L is 4n plus 2, then you will have this value, and H plus K plus N is 2n plus 1, you will have this value. So, these now are very special to zinc and sulfur. The general systematic absences come from this expression. So, one can calculate this expression, and we know that H plus K, K plus L, L plus H should be all even, then only we will get these reflections coming up. Among these reflections, because zinc is at 0 and sulfur at 1/4, 1/4, 1/4, that happens to be special positions in that space group, you will get additional absences, and they look as though they are systematic, but they are systematic only with respect to the atom positions. They are systematic of course therefore to the special positions in the unit cell. So, let us go back to the discussion on the special positions for a few minutes, because I think we discussed it some time ago and probably you would have over the days would have forgotten. So, the special position, when we discussed this special position issue, we found that the number of equivalent points, suppose P21 upon C we take, 4 equivalent points are there. Now, if the special position is there in the system, which is there, it is let us say sitting on the mirror symmetry, then the number of equivalent points will get reduced to 2. So, that means what was 4 before has now reduced to 2. So, the atoms are now restricted by the symmetry again, and that symmetry restriction is coming due to the presence of the 2 unscrew and the C glide. So, whenever we have again translational symmetries associated with the space groups, we will get special positions. We do not get special positions, for example, in case of P1, but we get special positions in P1 bar, because XYZ and X bar, Y bar, Z bar now can give rise to several centers of symmetry positions which are independent of each other. And therefore, if the atoms sit there, they are very special. In other words, they will give Z equals 1 rather than Z equals 2, and that gets reflected in terms of the systematic absences we see. So, these are not now to be called systematic absences. What we should call systematic absences are with respect to the crystal system. So, if it is a F centered lattice, whatever are the systematic absences associated with the F centered absence has to be checked. But then if we find additional systematic absences like what we see here, the special conditions, there are 3 possibilities in which the reflections can occur, and those 3 are indicated here. Only those reflections will come because zinc and sulfur are sitting in special positions in the F lattice. So, F lattice anyway exists, over and above you will have additional, as though they are absences, but they are not really absences, they are additional conditions over and above the conditions that are present in the F lattice. So, when we re-examine the international table entry, we will see what is the effect of special positions and how additional symmetry elements develop because of that effect. So, this is something which we have to keep in mind, and then we will come back and revisit it when we re-examine the international tables. So, what we have done so far is therefore to take the phase centered lattice, find out how the systematic absences come up, and then we took the example of zinc sulfide, which is very special because zinc and sulfur are sitting in special positions, and we worked out the possible systematic absences as a consequence in the F centered lattice. So, now we will have to see how to evaluate these or observe these systematic absences. So, let us now generalize it. Once we generalize it, we see that the systematic absences can be put in this form of a table. So, whenever we have a primitive lattice, we have no systematic absences. Primitive lattice can exist in all 7 crystal systems. So, in all the 7 crystal systems, we go ahead and collect the data. We look at all the HKL reflections, try to align them with respect to HE1, HR, KE1 and so on. And when such an arrangement is done, we find that there are no systematic absences in those reflections. Then we say it is a primitive lattice. So, the primitive lattice therefore will have no systematic absences. So, space groups like P1, P1 bar, P2, PM, P2 1 by C will have systematic absences, not because of the centering, but it will have systematic absences due to the 2, 1 and C, which we will examine later. Okay. At this moment, whenever there is a primitive lattice, systematic absences will not occur in general reflections. By general reflections, I mean H, K and L all having values. No projection reflections and no axial reflections are considered in this evaluation. The projection reflections and also the axial reflections may come as a consequence of centering. That was indicated to you when we discussed the C centered lattice. I told you that there is a, suppose there is a HKL which is 1, 4 and 0. So, that is actually a projection reflection, but what is important is to consider the addition of 1 and 4, and I said 1, 4, 0 is absent. So, that 0 there is actually referring to a projection reflection 1, 4, 0, but we are now considering the systematic absences in the overall HKL. So, we call these as general planes. So, under the general planes we also have the projection reflections as well as the axial reflections. So, when you have a centering of the lattice, you will have both of these coming up, and that you must remember, and that is something which we have to evaluate. So, when we analyze the data, the way in which we analyze the data is we put the crystal, X-rays come through, do the scattering. I will keep on repeating this whenever required. So, we get the scattering, and when the scattering occurs, we get the reciprocal lattice points. We index the reciprocal lattice points, we measure the intensities of the reciprocal lattice points. Then we organize the intensities in a certain order, let us say even reflections, odd reflections and so on. Then if there is a systematic absence coming in the general HKL reflections, then we will be able to identify the presence of centering. It could be one of the phases centered or all phases centered, it could be body centered and so on. So, whenever such a thing happens, we should have systematic absences. So, this particular table which I have given here tells you what are the types of systematic absences that occur when these coordinates, there is a mistake in the textbook, it should be lattice points, E is not there, it is C, LATT, IC, and there should be an E after that. So, C is missing here. So, it is okay, I have copied it from the textbook. So many, almost all the equations I have copied in the textbook, because I thought that if I write the equations, you know my handwriting, and that will be terrible. And if I prepare the equations, that will be an enormous effort for me, number one, and number two, it may not be, it may be more error prone when we prepare it ourselves. So, best is to take make sure that there are no other serious errors in the textbook and take it from there. And so, this has been taken from the textbook of McKee and McKee, and in fact, most of the equations which we have shown before are also coming from the textbook of McKee and McKee. So, let us now examine this table once more, so that we have now a complete hold on systematic absences coming due to centering. And I think that will take us to one particular stage where we can now diversify and see how the structure factor behavior comes, and then take up the systematic absences which come due to the axial systematic absences, the 2-1 screw as well as the glide planes. So, let us see how this appears. So, the primitive lattice, no systematic absence, you are very clear about it. So, if it is a centered lattice, we will have coordinates of the lattice point 0 0 0 and 0 half half. So, since the half is associated with the k and l direction, we will have k plus l odd reflections absent. So, only those values for k and l, we will have when it is even, we will have the reflection coming, otherwise it will be absent. I do not think I need to take an example to illustrate it. You can take some HKL examples to find out how this systematic absence is coming. B centered lattice likewise, and C centered lattice likewise, and F we have learnt just now. Here I have written the English explanation, HKL neither all odd nor all even. That means they have to be either all odd or all even to get the systematic presence. So, they will be present only, this is systematic absence. So, we can say neither all odd nor all even. So, the I centered is fairly straightforward, H plus K plus L is equal to 2n plus 1. Now, these systematic absences occur in all general reflections, be it projection, be it axial, it will occur in all HKL reflections. So, we have to consider all the HKL reflections in this particular case. I have given here 2 additional entries. We have not discussed at all in detail the rhombohedral and the hexagonal systems, because I just thought that this is slightly away from the plan of this course. However, we should remember that though symmetry also occurs, and in fact there are many materials which go with a rhombohedral symmetry. But there are many systems which go into hexagonal symmetry, particularly when people are talking nowadays about organic ferroelectrics and so on. There is a large number of compounds which go with hexagonal axis, rhombohedral cell but hexagonal axis. Okay. So, the hexagonal system therefore will have the coordinates of the lattice points are 0 0 0, 2/3, 1/3, 1/3, 1/3, 2/3, 2/3. In the case we have a rhombohedral setting of a hexagonal lattice. What I mean by that is that we have a rhombohedral system where A equals B equals C, alpha equals beta equals gamma, not necessarily equal to 90 degrees. So, effectively it is a distorted or pushed around cube, it is not a distorted cube, it is a turned around cube about a given axis. So, we will have therefore 3 values coming up for equivalent points of the coordinates, and therefore we have 3 lattice points, and therefore the systematic absence will come up as minus of h plus k plus L equals 3n plus minus 1. So, this is a very special case, we are not going to discuss it in detail here, but you should know that systematic absences can occur in a rhombohedral system, not in a hexagonal system, and particularly when the rhombohedral axes are referred to. Straight away if we describe the system in rhombohedral axis, then there is no. But if we describe the rhombohedral axis in a hexagonal system, that means we have a rhombohedral system, but we say A equals B not equal to C, alpha beta are 90 degrees, gamma 120 degrees. That is the unit cell we fix. That means we now have actually a rhombohedral cell, but we have fixed it in a hexagonal lattice. If we have a rhombohedral cell and fix it in a hexagonal lattice, then we have this problem, and this problem is because the rhombohedral axis now will show coordinates of these 3 positions, and that is the property of the rhombohedral cell. It is a special case of the hexagonal lattice. All hexagonal lattices will not show. So, in principle if we have a hexagonal system which is indexed as a hexagonal system, you have A equals B not equal to C, alpha beta 90 degrees, gamma 120, and then it shows rhombohedral symmetry, then you will have these systematic absences. So, this is very interesting. Suppose you want to find out the crystal system whether it is hexagonal or rhombohedral, you use this test. So, you use this test, if you see these systematic absences, it is rhombohedral axis, then you go down and set it to rhombohedral axis, then you have no systematic absences anymore. So, this is a way in which you can actually distinguish the rhombohedral axis with respect to a hexagonal system. So, this in a nutshell is what we see for systematic absences which are displayed by conventional lattice types. Now, let us go further and see what we have further to offer from X-ray diffraction. You see, we are talking about structure factors, the systematic absences in structure factors and so on. So, what we now do is to see what is the way in which structure factors behave. You see, we have seen the intensities how they behave. In other words, we have seen that when you do an X-ray diffraction experiment, I have already mentioned several times that the intensity of HKL will be equal to intensity of H bar, K bar, L bar, and that we call as the Friedel's law. That means that we have the 2 systems where we can now take the HKL reflections we have observed. It could be centered or face centered or body centered, those systematic absences will be there. But for any HKL measurement, if you also measure H bar, K bar, L bar, these 2 will always be equal as far as intensities are concerned, and that is the Friedel's law. Of course, Friedel's law can also be violated, and if this equation is not satisfied in a certain circumstance, we now invoke a situation where the electrons are now inside the crystal systems are now very close to the incoming radiation frequency. The incoming radiation has a frequency. We are ignoring the frequency change because we assume only coherent scattering. But what happens is, if the frequency is very close to this, the atom now absorbs the X-rays, because it does not know the difference. You know, there is a frequency coming, that frequency matches the frequency associated with the atom vibration or atom the K shell of the atom and the nucleus transition. So, if both are same, the waves cancel each other out, and therefore, you will not get any diffraction, you get severe absorption. At that situation, what happens is the electrons do not know what to do. See, the K shell electrons, you see the characteristic X-rays we get for copper, which we discuss as 1.54 or 18 angstroms, or molybdenum 0.7107 angstroms, they come due to the fact that we say it is K alpha radiation. That means the K shell electrons are the ones which get knocked out by the incoming X-ray. This is known as Mosley's law. I do not think we will have time enough to do it in detail, so I will measure it now. In the next few minutes, I will do the orally I will explain how the Mosley's law comes, but I think it is something which is very fundamental and which can be easily understood. So, let us say we have an atom inside the crystal, okay, and copper radiation is sent inside the crystal. I will make it as simple as possible. Copper radiation is sent inside the crystal, and then there is a nickel atom which is the next fellow in the periodic table. By the way, you must all remember and appreciate that this year is the year of international tables. So, United Nations have decided to call this year as the year of international tables. So, this is a real recognition for the work done by Mendeleev and the periodic table. Now, the fact that we have scattering factors, structure factors, intensities are all due to the fact that we have electrons, we have nuclei, we have different kinds of elements, and therefore, our scattering depends upon the different kinds of elements and the amount of electron density that is associated with them. All these are present in the periodic table. So, periodic table is in fact the fundamental requirement for any of these courses which we discuss this way. So, it so happens that this year is the international year for periodic table. So, lots and lots of international level activities will be organized. Maybe in the next part of the presentation, maybe I will show you a picture of Mendeleev with his periodic table, just to remember that it is the year of periodic table, just in the passing. It is not relevant to our course, but obviously it is relevant to our course because we are dealing with atoms and the electron density associated with atoms. So, I thought just as a memory I will show it. So, we will see now what happens to the structure factors. Intensities we know become equal. So, if you have a reflection plane which is 1 1 1 and a reflection plane which is -1 -1 -1, the intensity from this will be equal. I was talking about the violation of this intensity. The violation of the intensity comes because the absorption edge associated with an atom inside the crystal is very close to the incoming radiation. Then what happens is that the K shell electron should get knocked out from the incoming radiation, and then there should be a transition from the K shell, from the L shell to the K shell, and that transition gives rise to the characteristic radiation, which is 1.5418 angstrom, which we use. There are 2 electrons in the K shell, and therefore, we have effectively 2 radiations that should come, one for the one electron, the other for the other electron. But the 1 and the 2 electrons are not distinguishable, and therefore, when we get this diffraction coming out, we will get the alpha 1 and alpha 2, which are very closely spaced. So, for all practical purposes, we decide to use them as an average alpha. So, when this is happening and if it is close to the absorption edge, the 2 electrons which are now getting knocked out, they do not know what to do, whether they should stay with the incoming radiation and get out, or they should go now and generate the characteristic radiation. So, the consequence is these electrons now reach relativistic speeds. They reach relativistic speeds, they do not know how to go about, and this whole scattering now becomes anomalous. And this process, this methodology is called anomalous dispersion. And when anomalous dispersion occurs, it will occur in any crystal. It will occur to a very small extent, so we can ignore it. But if we do very accurate measurements of I of HKL and I of H bar, K bar, L bar, every atom is associated with an anomalous component. And this anomalous component can also be with respect to the organ diagram. So, we can have both real and imaginary components associated with this anomalous scattering. And anomalous scattering is very useful to determine the absolute configuration of a crystal. So, we will discuss it when we come towards the end of the course. I do not know whether we will have time enough to discuss such details, but essentially we will mention how to determine the absolute configuration for sure. And when we do that, we will bring in and invoke this variation, or in other words the violation of the so called Friedel's law. So, we will stop here.